I think that AI is just another tool that engineers will have to use in the future. So for us, I guess AI is just like maybe down the road, finite element simulations have been, is like a vehicle to free engineers from simulation, from repetitive tasks. And I think the role of an engineer will maybe change a little bit. So we will maybe use artificial intelligence in order to come up with better designs or to come up with a better, faster prediction or manufacturing for parts. But it will never replace engineers, in my opinion.
Welcome to episode 75 of the Engineered Mind podcast. I'm your host Yusuf, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I'm very excited to welcome Moritz Maier on my show. As a technical consultant in the field of additive manufacturing and generative design, Moritz leads ELISE as a managing director on the way to develop software for generative engineering. Using ELISE, engineers and designers can visually program several engineering steps and even digitalize a complete product development process. ELISE is an open platform, so you may even include third-party software here. In this way, complex processes can be run through automatically as part of an optimization. Automated product development with generative engineering brings you faster to your goal with a pinpoint landing of the result. In this podcast on generative design and engineering, Moritz and I talked about augmenting humans by generative algorithms, speaking the engineering language with an anecdote. We talk about the topic low code versus no code. Moritz gives us an example of the ELISE workflow in generative design. We will define what the term technical DNA means. Moritz and I discussed the controversial topic if AI will replace engineers. Moritz will give us an outlook to generative engineering in 30 to 50 years. He also gives his top 3 tips for founders. And last but not least, we will discuss the working culture and principles of ELISE. Ladies and gentlemen, here's my podcast with Moritz Maier. Hey Moritz, welcome to my show.
Welcome. Hi, Yusuf. Nice to meet you.
Nice to meet you too. So today it's all about generative engineering. But before we jump into this very exciting topic of generative engineering, what it actually is and what actually the startup that you've built is doing for engineers, can you talk a little bit about yourself, what you're doing and who you are?
Yes, of course. I'm Moritz, one of the founders and managing directors of ELISE. I originally studied aerospace engineering on the road in Stuttgart, south of Germany. And I guess during my last lessons in the studies, I was listening to a professor talking about a topic that is called biomimetics. So the idea of learning from nature and transferring the ideas of nature to technical principles. After the evolution had like hundreds of millions of years of time of learning and optimizing itself. And this lesson totally fascinated me because innovation that comes from nature and innovation that converts to the technical environment was like absolutely amazing to do. And so I decided to do my PhD in this area, went up north to Germany and Bremerhaven, and tried to investigate how engineers are developing technical products. A very fascinating topic. So the ideas of product development processes and methods and tools and everything that is kind of like involved in such a process. It's highly complex and totally cool to work in this field and also to innovate this field. And this was like a couple of years ago, so roughly like 14 years ago now, where I've been also working at the Research Institute. It was like a time at the Alfred Wegener Institute where we did like fundamental research on biomimetics and tried to go on with engineering services for mostly automotive industry, aerospace industry. And that's how we also get started of working in this field and trying to challenge the field, I would say.
Very interesting. You talked about this generative engineering aspect of like human-inspired generative design. Can you walk us a little bit through how, for example, your startup is helping engineers to kind of augment their creativity by using generative algorithms?
Yeah, so let me maybe like give you a short introduction about how product development is done in the regular way and also what is like market standard at the moment. So during a development process, there are several like people involved, software tools involved, departments involved, and usually you start at the very beginning with an idea. So there's a concept, there's requirements. So maybe it's we want to design a car, electric car, should have a range of 300 kilometers, 5 passengers into the row should fit in. And with this concept idea, there is the first department coming up with a with the geometry. So coming up with the first principle in a CAD software tool, coming up with the package design, the loading design, maybe some requirements, some crash conditions in there. And once the first concept is born, you then hop over to the next department or the next experts, which are usually the physics simulation experts, trying to simulate the concept, whether it's good for the like aerodynamics or for the crash behavior or for the static mechanical load cases. And then things happen quickly that they say, well, your concept doesn't work like this. So you have to redesign. And so it goes back to the CAD department, the construction guys who have to change maybe the design or the material that was involved or another load path or maybe like the form to better fit the performance of the car. And so this process goes on. And the further down the road a project involves, the more people are getting involved. So after the stress department, maybe there's the purchasing department involved, giving introductions to the material prices or the big SAT databases where the suppliers are involved. And so you're getting more and more into detail. And the problem is that the farther down the road you are in the product development process, the more things you actually know about the product, right? You know, maybe, okay, I've opted for, let's say, carbon fibers at the very beginning. And at the very last of the process, we realize, well, it's too expensive. So I have to change the material. And of course, this inflects the whole product development process, everything that is involved. And this is why today we have this very iterative, very like collaborative approach of product development. And it's a very like manual work. So there are different departments involved. There are different experts involved. And from one department to the other departments, you usually have these meetings. You have the imports, exports, shipping around like Excel lists or PowerPoint stress reports. And this is just like the way we work. But to answer your question, it's becoming really like a slow process. And if you ask the question now, what would happen if, for example, a computer would assist this process? What would happen if a computer actually could find the perfect design and could iterate through these workflows automatically? Then we're talking about a process, at least in the geometry world, where we're talking about generative design. It's the idea that algorithms can find the right geometry coupled with the finite element simulation, so with the physics, and come up with a product process on its own.
Very interesting. And I really like how you laid it out, actually, Moritz, in the sense of that the traditional way is more like you have a sequential approach and a very serial workflow of engineering steps where people think about first you do this, then you do this, rather than actually thinking about how can a tool support engineers in a way such you have parallel processes. So product one starts, actually, the development of product one starts. And when you go back trying to iterate for product one, it could be that even product two already starts. So actually injecting with the software into this product development workflow is really, really important. What I would like to talk about is this collaborative aspect that you talked about, and it brings me back to an anecdote. I'm not sure if you ever heard about that. I think it was the first generation of the Audi TT, and I think 3 or 5 engineers died because I think the designer of the Audi TT back then said that the spoiler actually doesn't look very beautiful, so they wanted to get rid of it. And actually, the car didn't have enough downforce on the Autobahn, and I think that caused the engineers to then actually crash and then caused an accident. So actually, speaking the same language between designers, engineers, and across different teams is, I think, very, very essential. So let's talk about ELISE. How does ELISE now leverage all these pain points engineers have and help them leverage their work in product development processes?
I guess that's a pretty cool example with the Audi TT, because it feels like those guys have not talked the same language during the process. So if they have would known that the downforce needs to be there in order to make the car ride correctly, they might not like cut it off. So we think that there has to be a universal language for all of the people involved during the product development. So the people who are like coming up with designs, the people who are simulating it, the people who have like the purchasing prices in-house, they all should be connected so that an information that is maybe in some down the road departments is accessible to the very first concept designers instantly. So we're talking about like a data model that is universal for all the people involved. And I think if you look into the different types of data that have to be involved in the product development process, it's an insane amount of data types. It's either like cost data, it's stress data, it's geometry, it's maybe a machine learning data. It's like there's a huge universe of different types and all they have to be aligned. And so we thought, well, it cannot be like a simple like for example the geometry model or just like an integer model or something like this. It has to be something more universal. And we came up with the idea that it might be something like a programming language, which is also very common if you're talking to a software developer. Because if you think about how software is developed, also with huge groups of people working together, they all align on a common framework. They do object-oriented programming. They have the same language, so maybe it's C# or it's Python or whatever. But they're working in frameworks. They're working in subsidiaries, subversions. They're working with code fragments. And this principle is something which we think could be also transferred in some relations, of course, only to hardware developers. That's why we developed the first programming language for engineers. And of course, I cannot write code myself, and I guess most of the engineers don't neither. So we try to come up with a very easy to use language. So we come up with a low-code visual programming language. So it's basically a building blocks and wires that you just click into each other. And this makes things very easily. And people, especially engineers, can now create algorithms on their own without being experts and having an IT studies.
Yeah, very interesting. And I think even though, like, if you could program, you mentioned low code, there's always this distinction between low code and no code, but I think some people use it as a synonym. So if an engineer could still code, let's say I know a little bit of Python and I would like to inject a bit of code into my workflow, it's still possible, right, using your tool?
Absolutely. I think we should lower the barrier as much as possible, but we shouldn't like cut the ceiling at some point. So we believe that engineers still have to have the opportunity to extend the code if they're experts. So we provide, for example, a C# and Python interface natively, but also you can create your completely own tool stack and create own boxes and building blocks. So we try not to harm anybody without the boundaries. So being easy accessible, but also being open for the experts who can write code like you.
Yeah. What I really love also with your approach is like maybe we could talk a little bit in a few minutes in on the workflow, like from the start, from the beginning to the end, and how such a workflow would look like in ELISE. But before we go into that, what I really liked about your you talked about, Moritz, is that you can put all the forces into your system, all the CAD geometries that you have, all the complexity, like doing multiphysics simulation, talking about manufacturability, costs, and so on of the component. Like, how does it help engineers? Like, maybe give us an application use case of a customer, maybe where they really could use your technology and like had an ROI of at least, I don't know, maybe 50-60%. Not sure what numbers we're talking about here.
Yeah, so the use cases that our customers are approaching are like completely viable. So it really depends on the field that you're working. And you could imagine that if you, for example, go for, let's say, 3D printing parts, you need specific building blocks. You maybe need to have like a building block for topology optimization or for the simulation of the manufacturing process. And if you're opting for, let's say, more model-based system approaches, so for example, coming up with a whole hull structure of an Airbus plane, this needs specific other building blocks. And I guess this also shows like the variation of the different use cases, because in the end, it's just visual programming that we're offering. But let me maybe deep dive into one of these use cases. I want to highlight a use case that has been done by a Japanese automotive OEM, and they're building up like a steering knuckle for a car. This is basically the part where the wheel is connected to the chassis, and also the braking rim is adapted to it. And this is a very highly loaded part and a very compact part. It's like either a 3D printing part in the more like a small series production or a molding part. But the principles of coming up to the final design are quite similar. So you usually start with the design space. So it's basically the area where your product could like be filled in without harming any cables or wires or any other mechanical stuff in there. You need definitely the loading conditions, so the forces that is reacting on the field and the part. And you definitely also need like material definitions. You need like the amount of maximum stresses and need all these kind of boundary conditions. And then what usually happens is that we are taking all these data formats coming into our system, either from Excel lists or from CSV databases, JSON files, connection to databases. They are stored anywhere in the system, in the IT system of our customers. And we try to process those systems with maybe a first topology optimization. And to run a first topology optimization, you definitely have to start with the pre-processing first. So maybe this is the meshing of the design space, which our customers usually do with software tools like Ansa or with Hypermesh for coming up with the settings of the model. Then running maybe in topology optimization itself. Either we process, for example, OptiStruct solvers or Hexagon Emendate. So these are like one of the two software solvers that we have connected already. And usually what happens next is that you have to interpretate the designs. So because the topology optimization results are more like on a mesh basis, so they're like tessellated data. And usually this is like a real big effort to get it back to a NURBS geometry, which you can then remodel in your CAD software tools like CATIA, for example. And there usually our clients are using a so-called subdivision modeling technique, which is able to convert the mesh data back to the CAD model, to the NURBS geometry. Then, of course, once you're back in the CAD world, you have to do the final evaluation. If, for example, the eigenfrequencies or the nonlinear crash cases have to be really there. This could be done either in OptiStruct or in Nastran, ANSYS, Alestina, whatever is like the software that is involved in our clients' software stack. Yeah, and then you know basically if the design that has come up with the generative part from the topology optimization is something that worked out. You can then maybe go into the next phase, looking into the manufacturing process. So if it's 3D printing, for example, you want to identify the orientation of the part to have multiple parts in the building block form. You want to identify the areas where you need support structure. In this use case, the specific one, we also implemented an optimization loop, for example, to orientate the part in the right way, to be able to stack multiple parts in the building blocks and to identify the support structures, to minimize the work that has to be done after the printing. Then also very specific to the additive manufacturing area, you want to know if there is distortion during the process, if it's like laser beam melting. So we are connected to Amphion. It's like a process simulation software from Octon, and they are able to predict the deformation during the building process. And if you can predict the deformations, you can have like a pre-deformation in the original part, so that after the manufacturing process, you will end up with the original geometry. And yeah, this is pretty much it. So this is like the workflow that has been built up or more or less like documented in our software. And the great thing is that once you really digitalize all the steps, all the different design steps, all the different interpretation and logics, how to come from the very first requirements until the final part on the building platform, you have digitalized the whole product development process. And the beauty is that once the requirements change, so imagine you want to create the same like steering knuckle for a completely other car, you can rerun the whole process just by changing the boundaries at the very beginning, or maybe the design spaces. But 80 to 90% of the workflows could just be reused or recopied. And this saves a lot of time. So due to the fact of digitalizing of the product development process, this is really something where at least on average our customers save 90% in development time. And so also in this case with the steering knuckle.
This is so crazy, Moritz. Like while you talked about this, like I was getting super excited and pumped because actually seeing this, I've had a look at your demo, like being an engineer, seeing visually like these building blocks that you've talked about and like connecting those and what load cases you have and what kind of simulation you want to involve, like the topology optimization module that you can just connect with basically drag and drop. This is so crazy. And like, I think this is the next generation of like doing engineering. One thing you actually talked about is this, what I think you call technical DNA. So actually like the distinguishment between explicit knowledge and implicit knowledge, meaning that you have explicit knowledge in form of CAD data sitting around on a database, but also implicit knowledge in form of creativity of the engineer. So when we think about like the demography change of like old engineers retire, but they still have that knowledge left in the company as implicit knowledge in the CAD data. And I think exploiting that is really, really valuable. What's your opinion on that?
Absolutely a low-hanging fruit for us, and we definitely can bring value here. Let me give you an example from one of our customers. They have been building trucks, the body in whites of the trucks, and when you like have those profiles that form the body in whites, you have to do the welding lines. And this is something which is really like expert knowledge to define in which order you have to put the pipes together in order to have the correct welding line and correct welding order. And it seemed like that the old engineers, they had this expert knowledge, and they said, well, it's just my stomach feeling. I cannot like tell somebody how it's working. It's just I know how it's going. So what we did is we interviewed those people, and we tried to come up with a logic. So we tried to really dig down how they actually decide if the welding line should be in this run or in the other way around. And we managed to come up with a workflow, with a logic, with decision trees and with kind of like the expert knowledge digitalized, and programmed this in our software or pointed it out in our software. And the cool thing is, now you have this expert knowledge digitalized. You can copy and paste it to colleagues. And also if like the expert is retired, the knowledge is still in the company. And this is something where we see absolutely the future. Also our engineers, they are getting older and older, and they're of course getting retired at some point. And if you see, for example, how we've been able to, it's a little bit philosophic, how we've been able to like fly to the moon down in the 60s, 70s, and we are not anymore. And we have to reinvent the whole wheel because the generations, they just not lost knowledge. And I think if we could digitalize this knowledge and make it reusable for other generations or for the next generations of engineers, this is really something which I'm excited about, to save knowledge and to share it with colleagues.
I'm also definitely excited about that, Moritz. And people listening to this podcast right now might think, okay, this is super cool. You have this amazing technology and we have, I don't know, AI assisted systems, which is also integrated into your platform. But then an engineer might come, maybe people from the older generation, saying, okay, this is all fancy and stuff, but will it actually replace me? This is always a fear people have. AI will come and will replace my job. What's your answer to that?
I think that AI is just another tool that engineers will have to use in the future. So also let me give you an example here. One of our customers, he trained like an AI model to predict the price of a specific part. So they had all data, they put it into a machine learning model, and now this building block is available for all the engineers in the company. And they just can plug it in and they get like a prediction, I don't know, 95% certainty or something, what the final price would be. So for us, I guess AI is just like maybe down the road, finite element simulations have been, is like a vehicle to free engineers from simulation, from repetitive tasks. And I think the role of an engineer will maybe change a little bit. So we will maybe use artificial intelligence in order to come up with better designs or to come up with a better, faster prediction or manufacturing for parts. But it will never replace engineers, in my opinion. So if I look into the future, let's say maybe 5 to 10 years, I think engineers will become more like curators. So they will supervise the algorithms that they have generated or build it up, or that have been like generated from artificial intelligence. But they still need to be there seeing if the algorithms are doing the right thing. Because there could be like biased training data, there could be like failures in the models. So I guess we will go into a different like job description of an engineer maybe in the future, but definitely will not like replace engineers.
Yeah, I would absolutely agree on that part. When we talk about the workflow in general, could you walk us through maybe one use case and walk us through like from the beginning to the end? Let's say I have a CAD model, maybe pick a specific example, and then walk us through how would this actually work? I import my CAD model, and then what would be the next steps?
Yeah, definitely. So you can start either by importing a CAD model that has been generated in a legacy CAD system, if it's there, or you can also model the whole geometry in our system. It depends a little bit if you already have data or if you are starting on a blank sheet design. Maybe let me give you an example of a bicycle frame. This is very, very easily. So you might have maybe not an existing CAD model, but you have your wheels and your parts, your saddle and everything that is like in place. And you want to come up with a frame design. So you maybe only import the design space, because this is something you know where the size of the frame and these kind of stuff. And then you start usually by modeling all the mechanical loadings conditions for the first finite element simulations, because usually people are not starting with a parametric CAD drawing. They want to have like a hint where the mechanical properties should be placed, and if it's like a wheel, like a rim design, or if it's more like a beam design, or if it should be like some kind of ideas. And so they're using topology optimization, most of our customers, to get an idea for a first like design iteration. So what you then would do is you model your whole like FE setup and you plug in the topology optimization cell. And this cell will give you a first indication in which direction your design should go. And once you're there, we usually see that people are either directly using the result, if this is for 3D printing or for molding, and if it's more for, let's say, a sheet metal design, or in our case for the bicycle, it would be more like, let's say, a welded tube design. They try to interpretate this design from the topology optimization. We have some kind of tools in there, for example, to identify the middle lines of topology optimization, or to come up with like a blank sheet design. So there are some algorithms who could interpret the topology optimization design. And you can use them to, in the end, automatically generate a parametric CAD model, which is based on classical shells, surfaces, lines, and these kind of stuff. So once you're there, the next step would be typically to identify maybe the right wall thickness or the right parameters. Maybe you want to have like a big wall, a big tube, or a small tube. So you have some optimization algorithms involved, like, I don't know, sizing or shaping or just parametric optimization, that you can maybe run some design of experiments. Maybe you want to opt for some sensitivity analysis, to opt for different material types. So you can really play around with the design. And this is actually something which we see very often, that our customers are not like modeling one specific part. They are using the system to have creativity in the design process again. Because if you like automate the different design loops, and you can think of, oh, let's generate 1,000 design options for my bicycle frame, and I will select like the top 5 that I think are looking good, or they're just like good from the mechanical properties, and I can compare, let's say, carbon fiber design to steel design. And this is something I think which makes engineering really interesting again, to be able to be this like innovator of new things. And the algorithms that you have modeled in such a workflow help you to really explore the different variations of the design. So imagine, maybe coming back to the bicycle, you have opted for, I want to go all in. I want to have like a carbon fiber design. This is like the fancy stuff. It's my race bike. Then you select the design and you set up your final simulation for evaluation of the final design. So like the fibers and the lengths and everything, you set up the FE model, then go into some, let's say, really detailed FE simulations to really see if the eigenfrequency or the buckling analysis, if everything is like great in here. Yeah, and in the end, you end up with the final design. Maybe you want to opt some components in here. You could predict the price if you have like your historical data in-house. And then, yeah, you're ready to go. You're ready with the design. And usually what we see is that at the final step, the design gets exported again to the PLM systems like Teamcenter or Aras or Windchill, where you have like the versioning in the bigger companies.
I see. You talked about structural simulations, which can be integrated in the design process, meaning like you do an FE simulation, for example. What about aerodynamics? Is that also possible? Let's say you want to do a CFD simulation once you have your structure.
Mm-hmm. Yeah, definitely. So our approach is not to reinvent the wheel on every simulation. So we think that engineers should use the software stack that they are like used in the past also, because we are working with the big companies like BMW and Volkswagen, and they definitely have their software stack in-house. So also, if you're looking into some like customers like Airbus, for example, they have to use Nastran code for the possibility to have the quality assurance later for the FAA to be able to fly the way. So there are some requirements from our customer base that it makes necessary to use the existing software tools. Same with CFX, for example, for the fluid dynamics. So what we are doing in our software is that we remote control those solver technologies. So you can think about like adding a low code graphical user interface on top of the solvers, trying to like automate the whole process and taking care about the import, pre-processing, export, and post-processing, so that we have this automation of the different software stacks. But under the hood, there is still the solver code from these established codes. And this is the beauty. We're not changing the software tools, so also the results that pop out at the end are 100% identical if you would have done it manually. We're just sitting this meta layer on top, which makes it easy to use and to automate.
You gave us a little sneak peek on how the future might look like, Moritz. Where do you see generative engineering being in 30, let's say maybe 50 years? Maybe what's your vision?
I hope that we are somewhere in the area of Jarvis, if you know this, Josef, from Iron Man. So our big vision is that engineers in the future will use those algorithms like an assistant, basically. So we will see that like all next expert knowledge, whole data, everything is getting digitalized, and at some point we will be able to learn from this digitalized data. So if you think about having a common data layer over the whole process, like from the first concept design, all engineering construction work, all the simulation data, all the purchasing data, everything machine readable and in one common data layer, and also like connected of the different software tools, we don't have any silos anymore. So we have like a really like a transparent overview, a machine readable overview. And if we could now learn from all of these data, I guess this is something which really could be a whole data pool of the future to learn from. And at the end, maybe not in 30 years, but I believe in 10 years, so it's getting faster than this. We will have like a system where I can really ask, oh, what would be like the smartest construction or the smartest material if I want to achieve like minimum weight and I want to like optimize the part to fit my eigenfrequency of 50 hertz, for example. And I guess we're already seeing this. If you know maybe GitHub Pilot, for example, so the open AI that is based on the GDP3, they can write code basically. And in the end, that what we are doing is only code writing in the engineering field. So I deeply believe that this will be the future. And we as engineers hopefully will sit on these fancy walls and just like talk to an artificial intelligence at some point.
That would be so cool. Is there already something implemented such as a recommender system that we know maybe from Netflix or Amazon where it's like, maybe you should try this design space or like design with that load case? Is that already possible on your platform?
Yeah, that's already implemented. So we started, we found the first steps, I would say. So there's like a recommendation system that is also learning from the user behavior. So when an engineer sits in front of the software, our software learns somehow like which blocks are connected to which blocks in his working environment. And so the more usage is done by the user, the smarter the system gets. And it's really like predicting the next step. And our vision is that at some point we could not only predict the next step, but maybe the next 2 steps, 3 steps, 4 steps. And in the end, we can really like predict like possible routes of processes that could become next. And this is something where we step by step go forward to predicting the whole workflow at the end.
What makes me think about this whole things that you talked about, Moritz, is always brings me back to this documentary AlphaGo. Maybe you know that, like where the algorithm like did a specific move, which was so beautiful, nobody would have expected it. Now, my question would be, do you see like with algorithms that you just program from scratch, I would say, that sometimes you see designs that are copied from nature? For example, when we look at bone structures or like tree structures, they usually have like very specific forms to optimally redistribute stress, for example. Do you see that algorithms already do that? And where would the future actually bring us? Maybe completely crazy designs where like I wouldn't have designed that by myself, but actually the algorithm gave me that design. I'm like, hey, that actually performs way better in a real world than what I came up with, if you know what I mean.
Yeah, this is a good point. I guess we're already seeing this in the topology optimization. It's also so-called bionic design at the end. So if you are optimizing a design space only with maybe a minimum stress or a homogeneous stress distribution, you will end up with forms that somehow look very organic. So if you're, for example, optimizing just like a beam that is in somewhere in a wall, it seems that it feels like a tree afterwards. And I think this is also the very origins from the SKO method, for example, for the topology optimization. They try to mimic like tree growth, or they try to mimic bone growth. So ending up with a mechanical optimal form most likely has been doing the optimization in the evolution before. Yeah. So there are definitely some parallels. But of course, also like the material is completely different. So you cannot copycat it from nature, but it's definitely something that's already happened during evolution.
Have you seen customers or like any other users working? Did you see a movement going more to the cloud? Is it something that you can also do on your platform, like working in a cloud system?
Yeah, I would love to go to the cloud. I guess some of our, let's say, German and especially European customers are not yet ready for it. So I guess there's some kind of fear here. The United States are way more like advanced in here. So we see definitely more customers like in the USA or in Japan, for example, going into the cloud than in Europe. But definitely this will be the future. And our approach is to offer a hybrid system. So the software itself is like an on-premise installation. This could be like internally in your VPN connection, totally secured. But we definitely want to have the high-performance simulations, for example, for the crash simulations, to be run on a cloud server or on a high-performance cluster. So what we are doing is we're trying to connect those two worlds, being able to interact with cloud simulation and at the same time having your secure data in-house on-premise.
Very interesting. Do you feel like there's a bit of pushback maybe from the older generations? I'm not sure why I always come back to the older generation, but I feel like, do you think that's like when you talk about generative engineering, and I've seen that on Twitter, by the way, Moritz, that when you use that word generative, whether that's on an AI level, it's like, what are you talking about? Like, this is another topic. This is just a buzzword. What would you say to that?
Yeah, I totally agree. Yeah. If you go to the IT departments, especially in the big companies, it seems like there's a big fear, definitely. Yeah, totally agree. And generative doesn't make it easier. Yeah.
Yeah. How would you, maybe let's jump 2 steps back here. How would you actually define generative engineering? What is it essentially?
So our idea is going with algorithms to find the optimal design. And we've come up with this new category of software because they're kind of similar like generative design. And generative design in a nutshell is finding the optimal form based on algorithms. And we think that form is not enough. We want to have the whole product found by algorithms. And that's why we are talking about generative engineering, which involves the whole engineering process from the first requirements until the final like process simulations and manufacturing or cost simulations, everything connected in one place, but driven by algorithms. So we want to them algorithms to generate the whole engineering workflow. That's why we came up with this new category of software.
Interesting. And when we have a look, maybe I can, while having the podcast, maybe blend it into the podcast, maybe a visual. When we think about the product development process from the concept phase up to the prototype phase, where do you see the biggest benefit engineers have by using your product, ELISE?
If you have the chance to start from the very beginning with such a digitalized workflow, you have the maximum flexibility and the maximum freedom. So we can see, let's say, customers who are designing a completely new design, a new product that hasn't been there before, like an electric motor, for example. And if you like take into account all the different like parameters, we're calling it model-based system engineering in this approach, and you program the whole workflow, you definitely have the best options to end up with a perfectly optimized design. The farther down the road you go in your design process, full CAD already finished, you only can optimize little parts of it. So maybe some notch stresses, or you can optimize maybe a rip pattern. And this is not like a big thing. It improves the product, but it's not like the big thing. So to summarize, maybe the earlier you start, the better it is.
Yeah, got it. I'm 100% sure this question will come up, Moritz. How does your licensing work? And is there like a version for students that students can play with?
Absolutely. We love students, so our product is totally for free for students. Just give us a call or wrote us a mail and you get access to the software. Also, we have like nice student challenges down the road. So it's every 6 months we start a new challenge. Partner with great customers. At the moment, it's Ariane Space who have like giving a challenge for some Ariane 6 bracket to develop, and I guess also next year there's BMW coming and MAN coming for some nice challenges. So yeah, just get in contact with us. And for the commercial users, we offer a classical subscription-based access. So it's based on a yearly license. You can opt in. And yeah, we look for a licensing model which also gives you access to all building blocks possible, but not paying for all of them if you don't use them. So we came up with a token model. Maybe you notice it's like a virtual currency thing. You can just like opt for some kind of virtual currency and then take the building blocks for your processes as you want. So maybe in week 1, you want to have like a topology optimization. Week 2, you need a cost optimization, and you can just exchange the licenses. And this gives a great flexibility to our platform. And also our partners, like for example, Hexagon software could be accessed through this licensing model, which makes it really easy to use.
Interesting. Maybe we talked about the future, Moritz. In 10 years, people will be able to pay those tokens by Dogecoin. Let's see how that goes. that would be amazing. So,
do you have some Dogecoins?
I have a bit of them. Yeah. I'm not super much into crypto, but yeah, the petition. I'll put a link to a petition down in the description, guys. If you want to reach out to Moritz and be able to pay in Dogecoin, I'm sure we can arrange that. We talked a little bit about AI-based assistants, Moritz. Can you maybe, if we missed something when it comes to ELISE as an AI-based assistant, anything that we missed in that aspect? How it augments engineering workflows?
No, maybe one aspect that I could highlight is that we are seeing some different like personas working on these AI workflows. So we see that more like the data analytics experts working in really like Python and these kind of stuff, setting up the deep layers of the models. And they're really like deep down into the models of the machine learning. And on the other hand, we see the engineers who have maybe domain knowledge but don't know anything about the details of a machine learning model. And I think it's really necessary to bring those two people together to, again, close the silos, close the gap so that they can work hand in hand. And I guess we've made a huge step with our software. It will be released officially in June, so it's not public at the moment, but in 2 weeks it will be public. We will announce our machine learning kernel, and there I guess the gap could be closed. And we've already seen some pretty like stunning results from our customers, what they can do with the handshake between the data analytic people and the engineers. And together, if we combine those two worlds, that's really something which I look forward to see.
Yeah, super exciting, Moritz. And I'll put the link to your YouTube channel in the description. So everyone listening to this podcast, Elise also has a YouTube channel with very nice tutorials, even using the API, I think, which I think we didn't talk about yet. But yeah, maybe if I get my hands on Elise and maybe do a tutorial in the future on my channel, that would be awesome. Let's see what the future brings. Any last words, Moritz, from your side? Any motivating words to all the engineers out there wanting to delve into generative engineering?
Yeah, I definitely can invite you to join the journey. I guess, at least from my perspective, as I have been working with the software tools and the processes in engineering, it always was kind of like not intuitive and not flexible. And yeah, at least I think if we can make the step towards programming hardware, this is really something which makes fun, at least for me and our customers. And I could invite you just to join the journey, give us a call, get a free trial, and get your hands on. Yeah.
Very exciting. And of course, another question. You as a founder, do you have maybe 3 tips for people who want to build their own company?
Work hard.
That's a good one.
It sounds stupid, but at the very beginning, I found myself with this ideology. Oh yeah, let's found a startup. It will like go for itself, and it is not. I guess it's like something where you have to work with passion and you have to really like stay behind the idea. And yeah, just be consistent on the things that you're doing. Be focused. I guess this is one of the main lessons learned that I had to learn during the last years. So many ideas, so many great things to do, so many opportunities. But if you are not focused on one specific thing, you might get lost at some point, and this doesn't help your company to be successful. So being focused and being consistent on the things that you're doing is a great thing. And maybe third, listen to your customers. Sounds easy, but I think at the end, the product has to fit to the customer's need and not to your idea. And this is something which also we had to learn. It's like, of course, you have to educate the people, because you're reinventing the wheel, basically. But you definitely have to listen to their pains and to their needs and how also the usage behaviors of a new product. And this is maybe the biggest challenge, to somehow innovate and somehow bring something completely new, and at the same time take your customers with you on the journey, so that they can like say what's good and what's bad of the software, and if they like it or not, and how you can improve.
Very interesting. Super cool tips, Moritz. That brings us actually back to the beginning, like founding Elise in the first place. That actually emerged from having a customer pain point. Like I think you were doing consulting at the beginning, if that's correct, and then actually coming up with the idea of founding Elise in the first place.
Yeah, it was a long journey. So yeah, you're right. We did engineering services and consulting at the beginning. And at some point, we found ourselves in scripting and macro writing between the different software tools. And yeah, the customers at the end of a project, they were quite happy because we came up with a stunning result. But our team had to do the night shift. So it was like always up till late. And we were like totally motivated to make the customer happy. But in the end, if it would have been like a company, there was no like black numbers falling out of the game. And yeah, it was at some point, it was like Robert, a colleague of mine and head of code, who came to us with a software from the architectural world. And really, he really like brought this idea of low code into play. And he really like reinvented engineering for us. And at the beginning, we used it for our own, the software, to came up just with our engineering services, make it faster. And at some point, it was like this question from one of our customers: oh, do I have to buy always the engineering service from you, or could I use the software or the tools that you have developed for your own myself? And this was like something which we really thought, okay, this could be a tipping point. Maybe we should not offer the services. Maybe we should offer the product itself. And the idea was born, and this is like a long time ago. So it was like 11 years ago that this idea was born. So it was really like a journey coming from the first prototype over our exist funding, which helped us to build up the first beta phase, to learn from customers, then hopping into our first seed round with VCs, because we realized that we are not being able to achieve this on our own. We need definitely more help and experts and network and also some money. And yeah, it's been a long ride, and I guess it will continue to be very exciting and also very challenging.
Yeah, I wish you all the best, Moritz. That's for sure.
Thanks.
When it comes to actually, like a customer buys your software, whatever license they might use, obviously it's not mostly the engineer that's in charge of actually acquiring that software package. Do you feel there was kind of a pushback from engineers, or do you think that engineers would say, hey, this low-code thing is absolutely great. I'm not a big fan of scripting anyway, so I'm very happy to use your tool. Have you seen that, or rather the opposite in the industry?
I think engineers, they usually love it. Of course, there are some fear at the very beginning if you do not know the software, but once you have the possibility to really like put your hands on the software and maybe went through the first one or two tutorials and e-learnings, they mostly get very excited about the possibilities. And there's always like a really interesting moment when they are slipping their mind and say, do you think I'm actually able to do also this with the software? And then they just try it out, and it feels like they can do it right away. So this like moment if you realize, okay, I can program, you can program anything, I guess, huh? And if you have this playground of possibilities, this is really amazing to see this, and it is great fun to also like onboard and train the people. So from the end user perspective and engineers, this is something which goes fully automatically. But of course, if you're opting in for politics and strategy, so if you're looking into the decision making unit up in the more in management, we usually see like also politics in the big companies, like we have opted for like the software vendor X, so we are not wanting to put another software in our tool stack. So this is really like strategic and political here. Of course, it's for a reason. Do not want to have like multiple software tools that do not fit to each other, but this definitely makes things not easier to come in with a completely new approach in engineering.
That makes a lot of sense. What I really like is also that this ingenuity that people come up with once they're using your tool, because usually you say if you want to understand the problem, you code it from scratch, whether that's like a neural network with C or any other programming language, but actually using your tool and saving time in the development process, product development process, and using that delta, that gap actually for more creative processes is, I think this is actually such a cool idea. And actually what you're doing, Moritz, and I think we have to emphasize this, is you take all that complexity, that coding aspect on the lowest layer, and then all this node handling and like the geometry thing that you do, the topology optimization, everything in one packed software is, I think, something which we shouldn't neglect and actually appreciate. Because you have done all the work. Engineers don't have to reinvent the wheel. You reinvented it basically. So yeah, thanks for that, I would say.
You're welcome.
Cool. Last question, Moritz, and then we can wrap it up. I promise, because I have so many more questions. Working at ELISE, how is the working culture at ELISE? I'm sure you're hiring. How can people reach out to you?
Yeah, just drop me a line, Moritz at ELISE.de, if you're interested in to join the journey. When we created the company, we wanted to have fun at work, actually. So we tried to came up with a working culture and the company culture that is somehow like inspiring. I've had so many bosses in my past down the road that I would say, well, not optimal maybe. So yeah, we try to be very flexible. It's like remote working all the time if you're interested. We do not have any holidays like counted in here. We had tried to have as much as possible team events and team meetings, chat rooms. So if you also maybe have a look into our career page, there are consistently like the open positions. Some also interesting video that we have come up with the team. You might watch. And yeah, I could just invite to the journey. If you're into engineering at the same time having the entrepreneurial spirit to build something, it's definitely never gets boring, and we appreciate people that are like better than us. So come up with a completely new set of mind, a new approach of thinking. So yeah, do something new, reinvent, speak out loud if something has to change. This is something where we love to work, and we could also like invite people who are interested in joining.
Very cool. Moritz, thank you so much for that interesting podcast. I'm sure, let's hope there will be a second part in the future. And once you launch that ML kernel in a couple of weeks, I'm more than happy to share that on LinkedIn, and we'll be in touch anyway. And I'm more than happy to get my hands on ELISE in the near future. With that being said, Moritz, thank you again, and we'll see each other on, as I said, LinkedIn.
Thanks, Yusuf. It was a pleasure. Take care.